So we've now come to the understanding that most reactions actually occur in two directions. They are reversible. There can be a forward and a reverse reaction. And we learned that when a system like this reaches a very specific state called equilibrium, there are a certain set of conditions that are occurring. So let's just say we have a reaction in equilibrium between A and B. We know that once this system is at equilibrium, or more commonly called dynamic equilibrium, we know that two things are occurring. The rate of the forward reaction, I'll label as A turning into B, is equal to the rate of the reverse reaction of B turning into A. These rates are equal, meaning the speed at which these reactions are occurring are equal. We also know that the concentrations of A and B are constant over time. This should be reviewed. It doesn't mean that they are equal to each other. You don't have to have equal amounts or concentrations of A and B, but we know that over time the amount isn't changing because the rates of the forward and reverse reactions are equal. So let's consider an actual example. Let's consider the equilibrium between N2O4, dinitrogen tetroxide, and nitrogen dioxide, 2NO2. Okay? This is a system that can be at equilibrium, forward and reverse reactions between the two. And let's say we set up this reaction in 3 different beakers. In the first beaker, we start with only NO2. So the concentration of NO2 is all we have. Okay, so for this system, we'll make NO2 red, and we'll make N2O4 green. What's going to happen over time is if we start with only NO2 in the beaker, in the reaction vessel, NO2 only, those molecules are going to start reacting, and we're going to have the reverse reaction occur. But then so the amount of N2O4 over time is going to increase. But we know eventually those rates are going to come to an equilibrium, and we're going to have equal, constant concentrations between the two reactants. So, for example, what this would look like on a concentration versus time graph is as time occurs, the amount of NO2 is going to drop slowly until it levels out when it reaches equilibrium. So again, this is NO2. At the same time, since we started with no N2O4, but it's being made as the NO2 molecules react, the amount of N2O4 is going to increase, and then eventually it's going to level off as well. So what we can see, what we need to be able to interpret from these graphs is at the point about right here where these lines become flat, where the slope of these lines is 0, that's where we know that we've reached equilibrium. Because we know the concentrations of each are not changing over time. We know that's true because the rate of the forward and reverse reaction is equal. Okay? Again, the system is not stopping. The reaction is still occurring once we've reached equilibrium. But since the rates of the forward and reverse reaction are equal, the concentrations stay the constant. What would it look like if we start with N2O4 only? Well, we start with N2O4 only, that's my green. N2O4, we're going to start with N2O4, the amount's going to drop down. Eventually, we're going to level off at an equilibrium. Once the N2O4 reacts, it decomposes into NO2. We're going to have NO2 that's going to start reacting with each other. So the amount of NO2 is going to react, and the concentration is going to increase until it levels off. Again, once these slopes of these lines right here are equal to 0, this is where we've reached equilibrium. Now, do you have to know if these lines cross or not? No, you don't have to be able to predict that at all. That comes from experimental data, which we can look at in table form, but you'd have to be able to translate that table form into a graphical form. A third possibility is if we start with NO2 and N2O4. Okay, let's just say we start with a little bit more of N2O4 than NO2. Well, we know that this reaction is going to occur in the forward and reverse direction. So maybe, maybe we get something that looks like this. Okay. Boom. Again, where red is NO2 and green is N2O4. Okay. Again, what we need to know is once we've hit the slope of 0 right here, this is where we've hit equilibrium. I want to emphasize one more time, you do not have to be able to predict, just given an equation, what these graphs would look like. You would have to have experimental evidence, experimental data of the rates and the concentrations of each reactant over time. But what we need to be able to do is if we see a graph like this, we need to be able to recognize when is the reaction at equilibrium and what is going on at equilibrium. Okay? We also need to be able to write something called the equilibrium constant, because we've talked about equilibrium in a very qualitative sense, but as we saw with those graphs, we can also talk about equilibrium in a very quantitative sense. Okay? So, how do you write the equilibrium constant? Well, if we have a reaction, let's just say general form of this, where the lowercase letters are the coefficients, the capital letters are the compounds. The equilibrium constant is abbreviated with a capital K. Capital K. And the equilibrium constant is the products over reactants. More specifically, the way this looks is it would be the concentration of compound C to the C power times the concentration of D to the D power over the concentration of A to the A power times the concentration of B to the B power, where again the lowercase numbers here all come from the coefficients in the equation. Okay, so we need to be able to write equilibrium constants for any given reaction. What's so special about the equilibrium constant? Well, what it does is, depending on its magnitude, basically the size of the number, we can determine, does this reaction favor the product side, or does this reaction favor the reactant side? And then when we revisit Le Chatelier's principle next week, we'll be able to predict more accurately and quantitatively exactly how the reaction will shift in response to a disturbance in its equilibrium. Okay? So for example, let's talk about an actual reaction. This is the general form you need to know, more specifically just the second part with the letters. We had our reaction of N2O4 was in equilibrium with 2NO2. So if I said, write the equilibrium constant for this reaction, equilibrium constant would be K times the concentration of the reactant. Well, we only have one reactant, which is just NO2. And the coefficient of NO2 is 2, so we need to write this NO2 squared all over the concentration of the reactant, which is only N2O4, the coefficient of which is a 1, so we just leave it as so. So this would be the equilibrium expression for this reaction. What we'll do in class is we'll talk about plugging in numbers and what the equilibrium constant actually tells us for a different set of conditions. But this is what you need to be able to do, is to write this given any equation.